great. Thanks, Chaim. So I'll be talking about dense matrix multiply and using Strassen's algorithm, particularly in parallel. And this is work I did while I was at UC Berkeley with Jim Dimmel, who you'll hear from on Thursday, and also Ben Lipschitz and Oded Schwartz. Okay, so the basic plan. So I'll show you a new algorithm. It's a parallel algorithm for Strassen's matrix multiplication. So we call it communication avoiding parallel Strassen, or CAPS. And I'll tell you that the CAPS algorithm is communication optimal. So it matches some lower bounds that we know of for Strassen. I'll also show you that it's faster in theory and in practice. And to back that up, I'll give you some performance data. And I'll also talk about some practical considerations for using Strassen and our parallel version of it. And so I hope by the end I'll convince you that Strassen's algorithm, it's not just a theoretical idea, something you learn in your first theory class. It's a practical idea, particularly in parallel. Okay, and so I hope that this work will be a little bit of a start to further exploration into tuning and the algorithm, making it robust, eventually getting to a library implementation. All right, so I want to start with a little bit of motivation. The first bit of motivation is just this great idea that Strassen had. So if you're not familiar with his algorithm, the basic idea is he shows that if you want to do matrix multiplication of 2 by 2 matrices, so very small, that you can do it with 7 scalar multiplies and a bunch of additions. So if you don't know it by heart, I put the algorithm on the left side here. And so you take entries of your input matrix. So say you're multiplying A times B. You take entries of the input matrix A and take 7 linear combinations of them. So one is A11 plus A22. You take 7 different linear combinations of elements of your B matrix. And if you do those 7 multiplies, so those correspond to the red Qs, and combine them in another special way, you get out the output matrix C. And so it's magic that all this algebra works, but you get the right answer, and the difference is there's 7 multiplies instead of 8. Okay, so that's great. That tells you how to multiply 2 by 2 matrices. The real beauty is that we can apply this recursively. We can use divide and conquer. So you start with n by n matrices, and you divide them into quadrants. And now this A11 is not a scalar entry in a matrix. It's now a quadrant of a matrix. And these additions and subtractions in the algorithm, they become matrix additions and subtractions, and the multiplies become recursive calls. Okay, so you write down the recurrence. There's 7 subproblems of half the size. And when you solve it, you see that the total flops, the floating point operations you do for matrix multiplication of size n by n is n to the log base 2 of 7. And that's a special number because it's less than 3. So the classical algorithm is cubic, and 2.8 is less than 3. Okay, so that's a cool idea. So that's motivation number 1. So Strassen says we can multiply matrices with fewer arithmetic operations. All right, but something you've already heard, and we'll hear again this week, flops aren't everything, right? So if we want to do things in parallel, we need to think about the communication that our algorithms do. So the cost of algorithms, the computational cost is important, but we also need to think about communication. And this is on sequential and distributed memory machines. So I'll be talking about the distributed memory case. So we've got a bunch of processors. Each has its own local memory, and communication happens over a network. But the takeaway is that as architecture trends continue, communication is only going to get more expensive relative to computation. Okay, so the first idea is Strassen shows us how to reduce arithmetic. But if we want to parallelize it, we can't forget about the communication. And so I'll be using this simple model that you've seen before. We'll think about the running time of the algorithm as a sum of 3 terms, 1 computational term depending on the number of flops you do, and then 2 terms that correspond to communication. So we think about both bandwidth and latency costs. Okay, so with that simple model, we've got sort of 2 motivations. 1 is we know how to reduce arithmetic. 2 is we got to think about communication. And when we first started thinking about a parallel version of Strassen's algorithm, we really came at it from the lower bound perspective. So I want to tell you a little bit about lower bounds that we know now for matrix multiply. Okay, so the story starts with the classical algorithm. Folks have thought about this for a long time. So the first result for lower bounds for communication when you do classical matrix multiply, go back to 1981. So if you're running on a sequential machine and you've got a limited cache or fast memory size and call that size m, then this expression gives you a lower bound on how many words you have to move in that algorithm. Okay, it looks like you can simplify this expression, and you can, but I've written it in a funny way for comparison later. Okay, so a little bit later, the result was extended to the parallel case. So there's a similar expression for a lower bound on the number of words you have to move. It's basically the sequential bound divided by the number of processors you're using. Okay, so that's great. Those are lower bounds for the classical algorithm. So it turns out that you can write down similar expressions if you want to run Strassen's algorithm, both in the sequential and parallel cases. So now this is why I've written it funny. So if you just change this 3, this log base 2 of 8, to a log base 2 of 7, that's the exponent in the arithmetic for Strassen's algorithm, you get the lower bounds for communication of Strassen. Okay, so these expressions look very similar. The proofs of these lower bounds are actually quite different. But the first thing to notice is that this lower bound on the left, because 7 is less than 8, is less than the lower bound on the right. But this is important. So Strassen originally showed we can reduce arithmetic with his idea. But these lower bounds, at least they suggest that you can also reduce communication. Okay, so that's what got us sort of excited, and we wanted to think about how to take advantage of this opportunity. So let me just say there are other fast algorithms out there for matrix multiply. If your fast algorithm has an exponent of omega naught in the arithmetic, that omega naught will probably show up in the lower bound just the same way. Okay, but I'm going to stick to Strassen for the rest of this talk. And let me point out there's one other lower bound that will become important. So in the distributed memory case, there's the second lower bound, which is both of these lower bounds are true, and the tightest lower bound is the max of both of them. Sometimes this guy's bigger, sometimes that guy's bigger. Okay, so that will come up later, and there's a similar story in the classical case. So the only difference is the red stuff. Okay, so we've got these lower bounds. We see that Strassen allows you, or at least allows the possibility, to communicate less than the classical algorithm. So are there algorithms that attain these lower bounds? Do we have optimal algorithms in all cases? And so the answer is, in many of these cases, yes. These check marks mean there exist optimal algorithms whose communication costs match the lower bounds. And the real question that we had, in the sequential case, the sort of natural way to write down the algorithm is great from a communication perspective. It's cache oblivious. Everything works really nicely. In the parallel case, it seemed less obvious to us. And we started looking around in the literature and actually didn't find an optimal algorithm. So what I'll tell you about today is the algorithm that we came up with, and the communication costs of this algorithm match the lower bounds that we found first. And of course, after we came up with the algorithm, and we're very proud of ourselves, we found a paper in the literature later that had the key ideas in it. But there's some new stuff in ours. So I'll focus on our algorithm and how it compares to the alternatives. Okay, before we get to algorithms, let me just say, because we were starting from these lower bounds, let me tell you some of the lessons that we got because we had the lower bounds before we started looking for algorithms. Okay, so the first one, which I think I've made the point already, the Strassen allows you to do less communication than the classical algorithm. So if you design an algorithm for Strassen whose communication pattern is based on the classical one, there's no way you're going to get to the lower bound. So that's the first lesson. Don't use a classical algorithm communication pattern for Strassen. You need to use the properties of Strassen's algorithm for an efficient parallelization. Okay, so that's the first lesson. The second lesson is that you want to try to use all the memory that is available. So I've written the tightest lower bound, which was the max of the two expressions I showed you before. And if you look at this first expression, it's not simplified, but if you simplify it, m will show up in the denominator with a positive exponent. So that means and m corresponds to the amount of local memory each processor has or uses. If you increase that value m, that means you decrease the lower bound. So if you use more local memory, there's at least the possibility that you can decrease the communication costs. Okay, and if you've got the memory, why not use it? It's not costing you anything else. So that's the second lesson we learned from lower bounds. Try at least to make use of the local memory you have. Try to use it in some good way to reduce communication. So there's a limit to how much you can do that. This second lower bound, which is also true, it doesn't have m anywhere. So if you let m go to infinity and pretend that your machine has infinite memory, there's a limit to how good that will, how much that will help you. This lower bound will start to kick in. Okay, so using those 2 lessons, we started looking for algorithms, and so let me tell you a little bit about what we came up with, but also some of the alternatives that we'll compare against. So I want to start with classical matrix multiply and basically a cartoon version of many good algorithms. So I'm going to refer to 2D or 2-dimensional algorithms for the classical, and the name comes from basically 2D distributions of the matrices. So you've got input matrices A and B and you're computing C. You distribute them across a 2-dimensional processor grid. And basically, algorithms, 2D algorithms work by somehow communicating blocks of A across processor rows and blocks of B across processor columns. Okay, it gets more complicated than that, but if you're familiar with parallel classical algorithms, think Cannon's algorithm, think SUMA, the more practical version, but this cartoon will suffice for now. There's actually also an improvement called 2.5D algorithms. Jim's going to talk a little bit about that on Thursday, so for now, all I'll say is when I say 2.5D, think somehow using a little bit of extra memory to reduce communication. So 2.5D is a little more efficient than 2D if you're able to make use of extra local memory. Okay, so if I say 2D or 2.5D, I mean a classical algorithm, nothing using Strassen. All right, so there's a cartoon of the classical story. Now let me tell you about a couple natural ideas for parallelizing Strassen's algorithm. So the first is what we call 2D Strassen. It's sort of combining the 2D picture I just showed you with Strassen. So the idea is you run this classical algorithm in parallel. But every time you have a local block multiply to do, instead of calling classical code locally, you just run Strassen's algorithm. Okay, so it's a simple enough idea, and as you can guess, the communication pattern is exactly the same as the 2D classical algorithm. The only thing you're changing is what's going on locally. Okay, so one of the first lessons we learned from lower bounds is you don't really want to do this. If you use the communication pattern of classical, you're not going to hit the lower bound. Okay, you do reduce computation though. So locally, when you do the block multiply, Strassen does allow you to reduce computation. So you get some win, but you're not really reducing communication. Okay, so I'm calling this 2D Strassen, sort of 2D at the high level, and then once you get to a smaller problem, then you switch to Strassen. Okay, so we can flip that idea and do Strassen at a higher level and a 2D algorithm underneath. So basically, if you look at the picture on the right, so these trees are representing the recursion of Strassen. So if you count, there's 7 branches on each of these trees. So if we run one step of Strassen, we'll generate 7 subproblems of a smaller size. And so it turns out you can run a few steps of Strassen and generate all these subproblems without any communication. So if you use the right data layout, you can generate a bunch of smaller subproblems to run without communicating. But then they're all going to be distributed across your entire set of processors. So as you go to compute each of these subproblems, you need to run a parallel algorithm, and you can run a 2D classical algorithm there. You have to run it a bunch of times, but the algorithm works fine. So it turns out, again, using Strassen here, you're reducing computation, but this actually increases your communication cost. The basic idea is you're running a classical algorithm even more times. So the communication increases actually exponentially in the number of Strassen steps you take. Okay, so this is a trade-off. You're reducing computation, but you're paying for it with more communication. We're often happy with the opposite. We're often happy to do a little bit more computation if we can save communication. This is not what we want to do. Okay, so neither of these approaches, these simple approaches, get us to the lower bound. I mentioned the 2.5D algorithms, so you can combine the 2.5D idea for the classical side in each of these cases. It helps. It gets you a better algorithm, but it still doesn't get you all the way to the lower bound. Okay, so after we looked at these and decided that we weren't all the way there, we thought, okay, we got to look at Strassen, think of a communication pattern based on the qualities of Strassen's algorithm in order to reach the lower bound. So let me just give you the main idea of our algorithm. So again, we're calling it CAPS. And the main idea is to figure out how to traverse this recursion tree of Strassen in parallel. And really, looking at every level of the recursion tree, we're going to make an independent decision. We're going to choose either to traverse it in breadth first or depth first order. So these cartoons show the 2 choices. So if we want to take a BFS step at a recursive level, that means we're starting with a multiply of A times B. Strassen generates 7 subproblems. And a BFS means we're going to run all 7 subproblems at the same time on disjoint sets of processors. So we'll have 1/7 of the processors work on this guy, 1/7 on that guy, and so on. Okay, so we've got to do some reshuffling to get that right. But it turns out this is very communication efficient in the long run. Okay, so BFS is what we want to do if we want to minimize communication. The alternative is a DFS. So that means we're going to solve each subproblem in sequence, but for each subproblem, we'll use all the processors. So we'll use all the processors to do T0 times S0, and once that's done, we'll do all the processors to do T1 times S1, and so on. So red here sort of means active at one time. Okay, so thinking about load balancing the flops, both of these are fine. Both we have perfect parallelism from a computational point of view. But I mentioned that in the long run, the BFS step will minimize communication. So why would we ever take a DFS step? And the reason is that if we want to do this BFS step and run all these problems at the same time, we need extra memory to store them. So each of these problems is smaller, but if you add up the space you need for all of them, it's a constant factor more. So this guy reduces communication, but you're paying for it with extra memory. But that's kind of a good thing. That's what we saw the lower bound suggested, that you have this trade-off. If you can use more memory, then you can reduce communication. So the algorithm is basically take as many BFS steps as you can, as many as your memory will allow. And a DFS step, because you're working on each of these problems in one time, you're working on only one of these problems at any given time. You don't need much extra memory. So if you're memory constrained, you take a few DFS steps to make the problem smaller, and then you take as many BFS as you can. Okay, so that's the basic idea, in theory. In practice, there's a lot of different choices you can make. So this plot is meant to show a particular example. So suppose we're going to take 10 recursive steps of Strassen, and we have 7 to the 5th processors. So that means we're going to need to take 5 BFS steps and 5 DFS steps. But when do we take them? So there's 10 choose 5 different interleavings of BFS and DFS. And this plot shows the trade-off between memory and communication. So along the y-axis is a metric of how much communication our algorithm will do. And along the x-axis is how much memory, how much local memory we'll use. And so you can sort of ignore the green dots because they're not paths, they're not interleavings we want. But the red and blue dots sort of navigate this trade-off between memory and communication. So if you've got this much local memory to use, then you want to choose this blue dot, and that minimizes communication. So this is the right thing to do in theory. And if you want to, so our theoretical algorithm sort of basically gives these red dots. But if you're a little more careful, then you can get these blue dots and navigate this a little more continuously. Okay, so a bigger tuning space in practice, but in theory, the BFS and DFS idea, it gets you to the lower bound. So let me just summarize the asymptotic costs, and I really just want to summarize by color. So blue is the lower bound that I told you about. Red means we didn't get to the lower bound, and green means we did. So this is just to convince you that, at least in theory, the CAPS algorithm is optimal, up to constants. And I should say that there's a similar story in the classical case. So there were these similar-looking lower bound expressions. There's some algorithms that don't attain those lower bounds, but the 2.5D algorithm does. So again, this lower bound is a little bit higher than the case of Strassen, but we do have optimal algorithms for classical matrix multiply. Okay, so that's the theory part, and so now I want to get to some performance data. Okay, so we wanted to run these on big machines, very, very highly parallel. And so we ran a couple of different supercomputers. This plot is a strong scaling plot on IBM BGP. And so let me try to help you digest it a little bit. So this is strong scaling. So the problem size is fixed for all points on this plot. The x-axis corresponds to number of cores. So as we go right, more and more parallelism. And the y-axis is a measure of performance, so up is good. So okay, the first takeaway is that, well, the red line's higher than the others. The red line's our CAPS algorithm, so that's a good thing. The second takeaway is that we're comparing against both classical algorithms and those that use Strassen to reduce the computation. And CAPS is outperforming them both. And in particular, this dotted line corresponds to the best any classical algorithm could possibly do on this architecture. So the dotted line is the theoretical peak, assuming you do the 2 n³ flops that a classical algorithm has to do. And CAPS is exceeding that peak. So it's exceeding the peak of the machine by cheating, right? It's doing fewer flops. But no matter how well you tune the classical algorithm on this machine, you can't cross this dotted line. Okay, the next sort of qualitative piece to pick out of this plot is that perfect strong scaling, which corresponds to if I double the number of processors, I'll cut my running time in half, it corresponds to a horizontal line in this plot. So as we move right, so we're sort of mapping to a horizontal line up to a point, and then we start to degrade. And it turns out that the theory tells us exactly why this has to happen. But before I show you how the theory compares, I just want to point out that if you care about the actual performance that our code is getting, we can draw another dotted line, which is the best performance we could possibly hope to do given the number of flops that we're actually doing. So we're above the theoretical peak of the machine relative to the classical flops. Relative to the actual flops, there's actually a lot of performance improvement left on the table. Okay, so even though we're beating classical algorithms, there's hope for further improvement. Okay, so just wanted to point that out. But now let's look at how our theoretical model matches to our actual performance. So as I mentioned, we can see some amount of perfect strong scaling, so close to a horizontal line. But after a certain point, because of the 2 lower bounds that show up, communication costs cannot perfectly strong scale forever. And so because communication costs don't perfectly strong scale, performance has to degrade somewhat. And so we're pretty close on this end. There's actually a bit of a gap between theory and practice on this end for high processor counts. And this is due mostly to network contention, which our algorithm doesn't really optimize for, and our theoretical model doesn't account for. So there's room for improvement, especially at the right end of the plot. Okay, so this is it's not a huge problem, but it's a problem that's big enough such that almost all these points are still compute bound. So these algorithms are still spending more time in computation than in communication. So the real win in the CAPS algorithms is coming from reduced computation. So because things are compute bound, because Strassen reduces computation, that's why we see a win over classical algorithms. But the problem is we're also comparing against other ways to parallelize Strassen. And so I told you that the previous approaches for parallelizing Strassen, they didn't minimize communication. And so it turned out that even though they reduced computation, because they either didn't help or increased the communication costs, they weren't able to beat the classical algorithm. So with the CAPS algorithm, if you are able to minimize communication, then you can hide it behind the computation and do much better than in the classical algorithm. Okay, so these are compute-bound problems we've looked at so far. And just to show you another plot, so this is on a Cray machine, and qualitatively the plot is pretty similar. CAPS, the red line, is doing better than the alternatives. Strong scales for a bit, but then performance degrades. This is another big problem. This is basically compute-bound. So the theory said that Strassen doesn't just decrease computation, it also decreases communication. So if we had a communication-bound problem, we should still see some kind of benefit. So we ran some experiments with much smaller problems. So these 2 plots are strong scaling, and now the dimension is fixed to be less than 5,000 by 5,000. And we're scaling up to many, many processors. And now the y-axis corresponds to time, not performance, and now down is good. And so on the left is an IBM machine, and on the right is the Cray machine. And so if the plot goes down, that means you're getting some benefit from more processors. If you got perfect scaling, that corresponds to this dotted line, and that's pretty tough to do on such a small problem. Okay, so there's not that much of a win on the Intrepid machine. The classical algorithm, this guy in blue, does almost as well. But we see on Hopper, so this is a log scale on the y-axis, that we see a benefit from the classical algorithm, and this turns into something like a 2 or 3x speed up. And this is not from reducing computation. So all the time and all the points on here are going to communication and basically latency cost. And because the Strassen's algorithm reduced the latency cost compared to the classical algorithm, that's why we get the win here. Okay, so the theory of Strassen reducing communication, that translates to the win in practice. Okay, but we see it, the benefit increases with P, so the best benefit is at high processor counts. Okay, so let me go on briefly to practical considerations, and in the interest of time, I want to focus on this last bullet. So a lot of people are worried about Strassen's algorithm. They feel like it's an unstable algorithm, and I can't run it because the errors will be catastrophic. So I want to try to convince you that it's a fair claim, but you shouldn't worry so much. Okay, so first of all, the CAPS algorithm is a parallel version of Strassen. It doesn't change the numerics at all, so we can really go back to all the things that people have studied for a long time about Strassen stability. And so there is a weaker stability guarantee for Strassen than for the classical algorithm. If you do a fast algorithm, you can't guarantee as tight error bounds. But the error bounds can be improved with various techniques, things like diagonal scaling. So there is hope. Furthermore, the bounds are better when you take fewer Strassen steps. And so this plot shows both theoretical bound and an actual bound. And along the x-axis, I'm varying the number of Strassen steps we take. So if you don't take any Strassen steps at all, then you're just doing the classical algorithm. And at the far right, you're doing pure Strassen all the way down to 2x2 matrices. And the theoretical bound in red, it looks bad, especially at the right end. In blue, for a reasonably conditioned matrix, it's not bad at all. At the far right end, you're going from something like double precision to single. But the good thing is, for performance reasons, you're never going to run Strassen all the way down to 2x2 matrices. So really, for a matrix of this size, you'll want to run about 4 or 5 Strassen steps, and the loss in accuracy maybe 2 digits in the worst entry in your output matrix. So it's not horribly unstable. There is a loss, but it's not as bad as you think. Okay, so let me just wrap up and summarize. I told you about the CAPS algorithm and that it's communication optimal. It matches these lower bounds that we have up to constant factors. I showed you that it was faster both in theory and then from the performance results, we see that it can be better in practice as well. And so I just want to argue that from at least these examples, we see that Strassen's algorithm, especially when we go up to high processor counts, it can be practical, and I think it should be used more and thought about more, and there's lots of room for improvement as well. Okay, thank you very much.
So we have time for one quick question.
So the algorithm